Hi folks, this video is about the specific tectonic hazards that occur when you get earthquakes, volcanoes and tsunami. We've looked in previous videos at the basics of tectonic hazards, how they form and where they form. We've looked at the theory, the tectonic theory that shows why plates move and therefore create the hazards. This is looking specifically at the hazards themselves. If you haven't watched those other videos, watch those first, otherwise this isn't going to make a huge amount of sense. We're looking at the specifics of earthquakes, volcanoes and tsunami. Let's start with earthquakes. When we're thinking about earthquakes, we're thinking about two plates or two pieces of rock. It might be on the same plate if it's an intra-plate earthquake that move past each other. So it could be a plate subducting, it could be a conservative margin where the plates move past each other, or it could be an intraplate earthquake where there's a break within the plates. Either way, pressure is built up because of plate movement, and then it's been released. And that pressure release causes an earthquake. The pressure is released at the focus or the hypocenter. Now that focus could be shallow, i.e. only tens of kilometres deep, or it could be very deep, it could be up to 500 or 600 kilometres deep. Either way, that's where the energy is released from. The epicenter is, if you were standing directly above it on the ground, that's where you would feel it as a person on the ground first. So you'd feel that first bit of energy. So it's directly above the focus, closest point to it. You might get a fault as well forming as the pieces of rock move past each other. You might get a fracture in the crust called a fault. You might not, you don't always. Anyway, energy is released from the focus outwards. Let me sort of get this pattern of waves moving out from the focus, and you can see that they're making their way through both pieces of rock. So you get these waves, they're called seismic waves, S-E-I-S-M-I-C. These seismic waves rippling outwards. And that's what you get when you feel an earthquake. So when the energy is released from the focus, you get four different types of waves, seismic waves, being released from the earthquake point. These are the P, S, L and R waves. And handily, they go in that order. You start off with a P wave. Now this is called the primary wave. I remember it's the pulse wave because you don't feel any shaking on the surface. You get it's like a pulse being pushed through. It just goes straight through the ground in a straight line. So it goes like this. So that's the P wave. Travels very, very fast. Travels about 8 kilometers per second. So you get this pulse that shoots through, and it can go through water as well, which is very important. Next up comes the S wave, the secondary wave. Now this is slower, this is about 4 kilometers per second. And this is the shake wave, as I like to think of it, because rather than being a pulse straight through, this one is the one that goes up and down. And this causes a lot of damage to buildings. Because if you imagine the building being there and the ground's doing that, it's going to do a lot of damage. So you've got the S wave coming along, and this goes all the way through the body of the ground. And it shakes up and down. So that's the S wave. Next up, you've got the love wave, the L wave. This is if you're thinking of a way to remember it, you can think of it as the level wave or the lawn sprinkler wave, because this one moves side to side, kind of like a lawn sprinkler goes side to side on a lawn, or if you like, if you're thinking a bit more sensible, goes in a level plane. It doesn't go up and down, it just goes in a level way. So this is working side to side along the ground. So this one's going up and down, this one is going sort of out and in, out and in. Like that. So you've got this sort of up and down from the S, you've got this side to side from the L, then you get the rally wave, and that comes fourth, and it's a bit like the S wave, this one, except it's more like an ocean wave. It kind of rolls. The base stays still, but it just kind of rolls through. So you've just got this sort of rolling wave. It's kind of making its way along. And it goes PSLR. So you start off with the pulse. That travels the fastest. That's the one that you can detect as well quite easily, and it gives you forewarning there's an earthquake coming. Then you get the S, where it's going up and down like that. You've then got the L, which is going side to side. And finally, the roll of the rally wave. And you can see why, in particular, these three waves are the destructive ones, because they shake the ground and they damage buildings. Some secondary hazards that can come from earthquakes. So after the earthquake's occurred and done its own damage, there are some other secondary hazards, one of which is landslides. All that shaking in the ground can cause the land to dislodge, and it slumps and slides down in a sort of rotated way. It rotates down off the hillside and slides. It's because the shaking makes it unstable and it slides, especially if it's waterlogged. That makes perfect sense. We can see how that happens. One of the other peculiar things that can happen, if there's a lot of water in the soil, particularly in places like Japan or California, around San Francisco, where land's been built out into the sea and the water level is very high, is that you get this thing called liquefaction, where the ground basically turns to liquid. All the shaking in the ground, it's shaking backwards and forwards, up and down. It's like shaking a pan of sand, and the sand, it all settles out, and the sand starts to settle down towards the bottom of the ground. And by settling down at the bottom, it pushes the water up. So the water makes its way up, and the ground at the surface just turns to liquid. And so the buildings, or cars, or whatever might be there, just disappear down into the ground. And as soon as the shaking stops, that water drops down and the sand picks up and it solidifies. So sometimes you find a house that's half buried in the ground because the ground is liquefied, it's sunk in, and it's re-solidified. So we can get landslides and we can get liquefaction as secondary hazards from earthquakes, as well as our other tectonic hazard, tsunami. Tsunami are caused by earthquakes, landslides or volcanoes, which all create enough land displacement to push a pulse of water through the ocean. When we're talking about land displacement, it's where, say in an earthquake, you've got a continental plate and an oceanic plate, and the subduction leads to the plates jerking past each other, and it displaces the land, moves it into the water and creates a pulse. A volcano or a landslide could do the same thing. And so this pulse of water moves through the ocean. Now, the size of the pulse will depend on how big the event was. If it was a very large earthquake, volcano or landslide, it's going to create a larger pulse. And a tsunami isn't just one wave, it's a series of waves. It's a wave train that moves together like a train as a block. It's not just little rippling waves at the surface, which as they hit the land, because it's only at the surface, they're not really too important. It moves as a whole block, and like a train, it actually rides up onto the land. Because it's being pushed by various waves, a big block of water rising up. And it rises up, crashes down onto the land, and then pulls back. So it crashes down, does a lot of damage, and then sweeps the whole landscape out to sea. And that's what makes it so destructive. It just pulls everything away. Now if you've got a long run up with lots of trees and things in the way, it'll take the energy out of the tsunami. But if it's a big tsunami, or there's nothing to defend against the waves coming in, then it's going to do a huge amount of destruction. You could argue they're one of the most destructive forces out there. Now tsunamis, you can't feel them, really, if you're on the top of the ocean, if you're in a boat, because you only get a tiny bit of rippling, because it's a pulse that moves through the water. It's the P wave, and S waves don't move through water. But you can feel the pulse coming in, and you can actually detect it on land, and you can feel it travelling through the moho. So you can get warning for tsunamis if you've got the right equipment. Now when it comes to volcanoes, there are various different types depending on what kind of plate boundary you're looking at. We go all the way from fissure volcanoes, which are the lowest magnesium content, have the highest temperature lava, and are the least explosive, all the way up through shield volcanoes, dome volcanoes, composite and cinder cone volcanoes, all the way up to caldera volcanoes, which have the highest magnesium content, lowest temperature, and are the most explosive. Basically, more magnesium and lower temperature go together, because if it's got more magnesium, it's picked up more impurities moving through the rock, and it's more viscous. So it's thicker, it's going to be cooler, but the thicker and cooler it gets, the more explosive that it gets. So you're more likely to get these kind of volcanoes at a divergent boundary, low magnesium, high temperature, low explosion, and these at the divergent boundary, high magnesium, lower temperature, more explosive. At a divergent boundary, you're more likely to get a shield type volcano, which means that you are likely to have lava flows as your biggest threat. Lava is going to be a great threat because it's going to be very high temperature and it's going to be very runny. So it's going to move very, very fast down the hill slopes. You're going to be able to, you're going to be able to see it coming, but you're unlikely to be able to outrun it if it's the thinnest, hottest type of lava. So these shield type volcanoes, like you get at divergent boundaries and places like Hawaii, lava flows are the biggest threat. Now if you look at a convergent boundary, or if you've got a much thicker type of magma, you've got less of a trouble with lava flows. If you do get a lava flow, it's going to be thick and it's going to be sticky and it's going to move slowly. So you're going to have much less of an issue with it. However, the big problems you're going to get are from the explosions within the volcano. When you've got a volcanic eruption, if you've got very thick, very viscous lava from very viscous magma, it can leave a plug in the vent of the volcano because it cools off and it dries and like a scab or something, it forms over the top. So the magma keeps pushing up and pushing up, creates a load of pressure. What then happens, of course, when the pressure gets gets high enough, it blows the plug out. Now this causes a huge cloud of ash. And you can get ash from divergent margins, as we found in Iceland, but that's a slightly different process which we will look at afterwards. But you get a huge amount of ash which comes out and rains down on the land below it. You get all this ash falling down. You might also get big chunks of rock, known as cinders, or sometimes bombs. Big chunks of rock, very high temperature, huge risk if you're close to them, because they can smash through buildings and through cars, and it can kill you if it hits you. But the other problem is the gas that's coming out. You get this superheated cloud of gas that mixes with the ash and it comes crashing down the hillside, moving at very, very high speeds. And this is called a pyroclastic flow. Pyro means fire, so that's related to the heat. And clastic is due to the fact that it's crashing, it's colliding, it's racing down the hillside. And that's very, very dangerous because it's hugely high temperature, and it will burn you very, very badly, and it'll kill you. So you've got pyroclastic flows, you've got the bombs and the ash, so bombs and cinders. And you have the, as I mentioned, the ash. So you've got all of these things have been ejected from the crater, and of course it'll blow pieces off the crater as well if the magma's thick enough. So if you're up there, you can actually have it blown from underneath your feet. Although if you were still up there, it would be very, very unwise. So you're less at risk of the lava here, it's more the exploded gas and fragments. Now, secondary hazards wise, if you've got a load of ash which has fallen on the ground and then it rains, all of that ash can form mud. And that mud creates it's a very fine mud, and so it moves very, very fast. It covers everything, and this is known as a lahar. L-A-H-A-R, lahar. It's very fast flowing. It can basically be a river of mud, so it can drown people, destroy homes, destroy buildings, certainly destroys cropland. So in the least developed countries, it's a huge issue. Now, with regard to these divergent boundary volcanoes, the reason there was an ash cloud in Iceland was because the volcanic eruption mixed with the ice and created a sort of aerosol, mixture of water and ash, which created basically a load of steam. And this was what got into the atmosphere and interfered with flights and things, because it got right up into the upper atmosphere and created a huge cloud. So ash clouds can be a secondary hazard from a divergent boundary, but they can also be a secondary hazard from a convergent boundary. Now, while we're thinking about Iceland and glaciers there, if you think about what would happen if a volcano erupted underneath a glacier, this is potentially a big problem, because of course if magma rises up, it'll melt a pool of water underneath the glacier, and that heat melts that pool of water, and that pool of water is going to get larger and larger until eventually it bursts out the bottom of the ice. Now, this is a vast amount of water that's being held there, so you get this huge rush of water which comes out. for the Glacial Outburst, or a Jökulhlaup from the Icelandic. Jökulhlaup, Jökulhlaup. This is a huge glacial outburst, massive flood, and it's a great risk to people and property if you get this huge outburst of water. And you get it a lot in Iceland because, of course, you have got a lot of volcanoes. It's a very volcanic area, and you've got a lot of glaciers in that area as well. Less so now than they used to be because of global warming, but I digress. So this is a very important hazard. So there you have it. Those are the tectonic hazards. We've looked at earthquakes, volcanoes, and tsunami, the different types and the reasons for the different types. We've also looked at the secondary hazards, the hazards that occur after these tectonic hazards, such as landslides, such as Jökulhlaups, such as lahars, and the links between earthquakes, volcanoes and landslides and tsunami. If you have any questions, let me know. Thanks for watching.